Hello everyone, we are the team from the Institute of Information Engineering, Chen's Academy of Sciences. Today, I'm presenting the work AE-Morpher, Improving Physical Robustness of Adversarial Objects Against LiDAR-based Detectors via Object Reconstruction. The presentation is divided into the following 5 key sections. Autonomous driving technique is being increasingly adopted worldwide. The major companies like Tesla and Huawei have entered the field and contribute to the growth of the market. As this technology advances, understanding the vulnerabilities within these systems becomes crucial. In this context, adversarial attacks on autonomous driving systems have emerged as a major concern. As illustrated in this figure, these attacks often involve misleading LiDAR-based detectors by placing a small adversarial object behind the target car, causing the detector to fail in identifying it, potentially leading to serious crashes. However, current adversarial examples lack robustness when transferred to real-world scenarios. The adversarial examples generated in the digital world often fail in the physical world. Why do they fail in physical environments? We then conduct a deep analysis. As illustrated in this figure, adversarial perturbations from adversarial objects are discrete, but the LiDAR are scattered and might not precisely hit the extracted spots. This means that LiDAR cannot capture all the details of adversarial objects. Consequently, this creates a gap between the desired adversarial point cloud and the one captured by the LiDAR, thus compromising the effectiveness of the captured point cloud. These two figures display the LiDAR-captured point cloud at different distances. As mentioned earlier, LiDAR beams can hit different parts of an object, resulting in differences in the final captured point cloud. This means that the distance between the LiDAR and these objects being scanned affects the shape and the accuracy of the point cloud, which is crucial for the effectiveness of the captured adversarial point cloud. Overall, the characteristics of LiDAR and the adversarial object cause a difference between the desired digital adversarial point cloud and the captured point cloud, which reduces the effectiveness of the adversarial object in the real world. Then, we will discuss how our system design addresses these challenges. We design a system, AE-Morpher, which aims to make adversarial objects more robust in the physical world. Our system consists of 4 stages: identifying effective vertices, constructing the adversary surface, constructing adversary object, and improving stealthiness. These stages transform an original adversarial object into a LiDAR-friendly reconstructed adversarial object. First, we use a raycast algorithm to simulate the LiDAR capture process, scanning the adversarial object from different distances to generate multiple point clouds. These point clouds are then fed into the detector to identify the most effective point cloud with the fewest points. This step helps fill out the signal points that contribute most effectively to the adversarial attack. This figure shows the original fit size and the filtered vertices. Next, we convert these effective points into adversarial faces. This increases the likelihood that each effective point will be hit, resulting in a more effective point cloud. A single face cannot exist in physical world, so we then need to transform these faces into a 3D object. This design makes the object more LiDAR-friendly, allowing it to be captured more accurately by LiDAR. To enhance the stealthiness of an adversarial object, we adjust this height. This adjustment helps balance stealthiness with robustness, because a greater height increases the LiDAR reflection area, which improves the robustness while reducing the stealthiness. Then I will introduce the effectiveness of our approach. Our evaluation is conducted in Opera 7 with the SVL Simulator. We equipped the target car with the original adversarial object and then with the reconstructed one. Then we replace the victim car behind the target car, move it towards the target, and record the frames where the target car was detected or not detected. Our evaluation shows that the attack success rate has significantly improved at various distances, demonstrating the effectiveness of our approach. We also evaluated cases where the victim car was not directly behind the target car, as shown in this figure. The attack success rate also improved significantly at different angles, further validating the robustness of our reconstructed adversarial objects. In addition to simulator evaluations, we also conduct real-world tests. This figure shows that the nighttime scenario. We place the adversarial object on top of the target car and use a 16-line LiDAR to move toward it. The captured point cloud was then fed into the point pillar model. As a result, we achieved an attack success rate of 71.4%. Additionally, the adversarial object was made from cardboard, costing less than $20. This figure shows the daytime scenario. We use a different target car with a corresponding adversarial object, placing it at the back of the car. All other settings were the same as that in the nighttime scenario. This time, we achieved an attack success rate of 18.8%. In conclusion, our approach has enhanced the robustness of adversarial objects by using LiDAR principles to reconstruct surfaces that align better with sparse LiDAR beams. This approach is successful in both simulations and real-world experiments. Additionally, our approach is cost-effective as it doesn't require expensive 3D printing and can be implemented with cheap materials like cardboard. Thanks for your listening. I help present the paper on behalf of the authors. If you have any questions, you can contact the author at this email. Thank you.